Good afternoon, ladies and gentlemen. Servus. Well, it's evening in our case, so.
And good morning for them.
And good morning. Well, I don't know if it is morning. Is it morning at you?
Yes, it's morning.
Okay.
First, I would like to introduce you. So welcome, grade 11 students. I'm thrilled to be here with you for the virtual visit to CERN, the European Organization for Nuclear Research. This tour is interactive, so feel free to ask questions anytime. Just raise your hand. Today, our guides will be Noemi and Zoltan. Thank you for hosting us on this virtual tour. And I now pass it over to them so we can start. Most nem hallak, le vagytok nyitva.
Sorry, I was muted. I'm not going to mute myself anymore. So, hi, good morning, everybody. I'm Zoltan from CERN, from, well, the continental Europe. I have three colleagues with me today. One is Noemi background. Also, we have two other colleagues. One is Derek, yeah, and Collin. They are going to help us today to go down to the so-called service cover underground, and we are going to have a tour around at TMS. Let's start with yeah, exactly. I'm doing the direction tasks today as well, but let's start with this little screen here. That's the landscape of where we are at this moment. That's I used to call it as probably the best place in the universe. That's quite subjective. What you might see here is the Geneva Basin. We have the Mont Blanc, the top of the Mont Blanc, top of Europe behind. Also, what you might see, the Lake Geneva. You might see downtown of Geneva here, the International Airport of Geneva. And even despite of the distortion, you might see that this yellow stuff is pretty big, even with respect to the runway of the Geneva Airport. We are going to talk about this, and especially one part of this today. That's the Large Hadron Collider. Obviously, we didn't mark it on the surface. That's a deep underground. And actually, we are going to start from here, that you might see CERN Meran, as it's written in this point. That's the traditional campus of the European Research Institute for Nuclear Research. Actually, Conseil Européen Recherche Nucléaire, this was the original name in 1954 when it was founded by 12 countries. Today we have, I think, 27. Am I right?
No, or 28.
I something like it. Fortunately, it grows every month, so it is very good. And actually, all the stuff that we started to have was first built on this campus. And actually, as the time went by, and as the energy of the particles that we smashed together increased, we needed to build bigger and bigger devices. The first big one that couldn't fit on the campus, even the enlarged campus, was the superproton synchrotron, this 7 kilometers long tunnel under the countryside, and connecting the original CERN campus to the, well, quite of a new campus of CERN that is entirely on French soil, named after the village nearby, Côte-Brefson. So now today we have two big campuses, and we have even more bigger accelerator that called the Large Hadron Collider that has 4 underground points. Well, let me just try to go there. Yes, exactly. So that has 4 big underground points where we populated detectors. Actually, it has 8 accesses, and out of these 8, out of the other 4, we have one for the particle acceleration, one for the particle dump, but I'm not going to talk about today. So we have 4 big experiments on the ground. Well, yes, exactly these ones. Two out of them, Atlas and CMS, are designed to make proton-proton collision, and we use them as a general discovery detectors, while the 2 others are more specialized. The ALICE is specialized for heavy ion collisions. This is what I didn't mention yet, that we collide not only protons in this huge accelerator ring, but every year for about a month. Actually, we are starting now.
Yeah.
We collide lead ions. Actually, not just lead, but also xenon. I think oxygen run we had this year. So heavy ions that are completely stripped away from their electrons, and with the collision of these guys, we try to make a new form of the new state of the matter that we call quark-gluon plasma. Today it is discovered, so obviously we know that it exists, but obviously its properties are still to be discovered completely. So that's why we have a specialized detector. It's called ALICE, a large ion collision experiment, or a LHC ion collision experiment. Actually, there might be 2 different things of this acronym. This is entirely built up for the heavy ion collisions. Apart from this, both Atlas and CMS has its heavy ion programs, so we are quite competitive. And there is another experiment, the 4th one, called LHCb, where it is named after the B quark. The B quark decay is very interesting in nature, as on one hand, the B detection is quite established. The other thing is that it decays mainly weakly, and that's a very interesting thing to explore, how the weak decay works. Probably you know that it also involves the so-called charge parity violation things. So this detector can tell us, hopefully, why only left-handed neutrinos exist in nature. Right. Actually, today we are more bound to the CMS, the compact muon solenoid. Compact as it is small, you see the person next to it is just a 4-story building size detector. And this is situated, if we go back, this is situated deep in France. You might see the French-Swiss border cutting through the countryside. Actually, we are sitting here on the surface in the control room of the CMS. And that's the point where I would ask Noemi to go around and show the control room and take the voice.
So I go with Collin, and then I can stay.
As you wish, gentlemen.
Also, if you want, you can.
Yeah.
Yes, please.
I left my safety equipment in the car.
Don't worry. I just got rid of my safety shoes. Right. So I let Noemi to take over.
Should we go underground immediately, or?
I would propose to go around in the control room first.
Round in the control.
Yeah, and show where we are. Let me just cut back here. And as soon as you send the picture, Noemi. Yes, it is better to show that than my ugly face. Yes. Right,
Okay.
Noemi.
Okay, then I talk, you muted. Okay, so we are in the CMS control room. It's quite large, and what you see here is the
I'm
so-called
sitting there.
so-called central area of the control room, and we have different shifters who has different part of job to do, and they have 8-hour
First
long.
of all, sorry for cutting in, Noemi. Let me just emphasize that we are looking for very rare events, as we call, very rare physics Therefore, we have to be able to take data 24/7 when the accelerator runs. So please take a look at through these glasses and regard all these things that Noemi shows through these glasses.
Yes, so this is why we have to run 24 hours per 7 the experiment, and we have different duties for different shifters. This is quite a big desk for the technical shifter. And this is the job of the technical shifter to make sure that the detector, the subdetectors are switched on, the cooling is okay, all the safety system is working correctly. If there is any fire alarm, he handles it. Also, he has some overview of the access to the underground areas. And he has a screen with lots of cameras which are installed in the experimental site, also underground, also inside the experimental cavern. So that's really close to the detector. Yes, maybe this is a nice picture. So this is really live image. And for going underground, we have some access pads, and so the shifter can see who is using it, who is underground. But the main importance is to know what is the status of the subdetectors, because the CMS detector is not one object, but it has different layers, different detectors, and it's a quite complex system. So of course, he can call experts for the subdetector in case of problem. And yes, this is a very heavy shift. We have also the shift leader, who is the captain of the ship. So he has to aware what is going on with CMS experiment and what is happening. He keeps contact with the LHC control room. And also the run coordination of CMS. We have here the data acquisition shifter. So this means that he's responsible when to start the data acquisition. In principle, we take data all the time, to run the detector, even when there is no beam in the LHC, because we can take the so-called cosmic run. And we like the ducks because the DAQ, it sounds like this rubber duck. So this is why we have. And here we see the imaginary green button to start the data acquisition. And
I just would like to make a remark here.
Okay.
What I didn't mention, I just told you that this is a compact detector of a 4-story building in size, but I forgot to tell you that we have 120 million data channels. That complicates the life a little bit. Indeed, also, there is another point that I didn't mention, that we get proton collisions 40 million times per second. So again, if you would want to understand why do we have this fuss around of shift leader, technical shifter, DAQ shifter, and the two others that Noemi didn't show yet, please take into account that we have an enormous system that we have to operate. Don't forget that this 100, each one of these 120 million channels need power. Many of them needs cooling, different types of cooling. They need to bring the data out somehow. And some of them also needs gas. So don't forget that this is an extremely complex system. The technical shifter's desk is so huge, mostly because of this, and also the other tasks that Noemi just mentioned, from the safety through the access to the technical infrastructure things. And also the DAQ requires a very skilled person as well in order to operate, again, because of the 120 million channels. And what I didn't mention as well, that if you want to have a synchronized data readout, you have to have the same delay on each of these data channels. I never wanted to hide that this is a complicated system. All right, sorry, Noemi, go ahead. It was just come to my mind.
Yeah, then you will talk about later about what is the trigger system because we have a shifter for that. But in a nutshell, the trigger, you can imagine that we have to filter the data. We have filtered this lots of channels to make an amount that we can handle. So it's a very complicated system. So we have a shifter for that, and this is the shift post. And also an important shift post is the DQM, which stands for data quality monitoring. So we want to make sure that what we record data is correct, is usable, and we can use it for offline analysis. So the shifter has plots and can pinpoint any problem with the detector, which can be a problem of the data taking of the particular detector, or can be a hardware problem of a detector. So the DQM shifter can alert the expert if there is anything bad in the plots. So that's the main shift post, the central shift post, and there is a person in these posts 8 hours long and 24 hours for 7. And we have also another part of the control room which is quite deserted because we are a bit late in the evening, but this is for the desk for the subdetector experts, and most of the experts are on call, and they can monitor the detector from home, or they can be wake up by the central crew. And during daytime, there are more people here because they can work from here and easily access the detector. And we have some big screens in the control room, which gives an
just
overview.
To amuse ourselves, apart from the fact that we want to know what is going on in the accelerator. So if you show the second, Noemi, that tells that now we are entering the ion physics. I mentioned that we will collide heavy ions, lead ions in this case, up to the beginning of December, I think 8th of December, 6 a.m. Geneva time. And today we are doing the transition to that. Actually, during the past 3 days, since Monday, we made a short technical stop to reconfigure the accelerator for that. And then now we have as I see, a cold checkout without beam. And as soon as it is done, we will inject the first beams in there. That's a very interesting period, even if I've seen it many times in my life so far.
Okay, so this is the LHC overview, LHC status overview screen, and that's also accessible. I think it's public web page, so anybody can.
It's
can
complete.
find
If
it.
you just type Vistar CERN LHC in Google, and the first hit will be this page where you can see it.
Status, and we have also. We also have a status screen for our CMS experiment. This is mainly for the data acquisition and which subdetector is in the run. And we have an event display, which is now a bit deserted because we have no collision. So I think that's all about the control room. I propose that we start to go underground, if you don't mind.
Sorry. Even though I promised that I will never mute during this session anymore. Anyway, so I had two statements. One is that we are going to lose Noemi on the way going down in the elevator. The connection will be lost. I will try to bridge it. The second is that if there is any question emerging, please don't keep it. Ask it immediately. So, all right. I see Noemi and Collin. Noemi, we are going to get dizzy a bit. Right, where you are at this moment. Noemi, I didn't want to lose her immediately.
I'm sorry, I'm just fighting with the new toy.
I think it is good as it is. Don't touch.
Okay, so we are approaching to the access pad, personal access door. I asked Collin to go ahead. So he has to badge with his dosimeter where he has his biometry data stored. So this door makes sure that only one person goes in and the person has all the safety courses done. So it checks the iris with this reader. So it was a success for him. So I tried to go in with the camera. It is not easy because it wants to detect that I go only myself and I don't bring in.
You have to cheat. That's true. That's obvious.
Yeah, because the door wants to make sure that only one person goes in. But I think I managed it. So then here is the eye reader, the iris reader. Okay.
For those persons who have seen the Angels and Demons, and now it is a evergreen movie, I guess, as it was filmed about 20 years ago. In this movie, something similar reader gets a role, to tell this euphemic way. I have to tell you that we use that reader. That's a real reader. But without spoiling the script of the film, I just would like to tell you that these new versions that we are using today are reading both eyes and also the blood circulation in them. Right. So they are in front of the elevator that will take them underground. Well, let me just check in the meantime.
Yeah, I just called the elevator and it has a display to show the position.
That's a simulated position, so don't get surprised. It doesn't go so fast. Right,
yeah,
it arrives at this moment there.
Yeah, and as soon as the door closes behind me, I will lose the connection. So I will ask you, Zoltan, to take over. So it's a quite big elevator and we have 3 levels. We go to -2.
Exactly.
Okay.
As the door closes, today at 1.9 meters. No, it's 2.5 now, where we lost them. But that's going to be just a temporary thing. But in the meantime, they arrive on the ground. Let me just show you. Let me just show you where they are and how the landscape looks like if you would look down. So they go down in the vertical shaft called PM54. Well, after the French name of the vertical shaft for machine, and the number 5 is the 0.5 where we are. That's a bit of a cryptic thing, but we all have to use these kind of things. So they go down in this way, in this vertical shaft, into this zone that is called underground service cavern. Unfortunately, they will not have a chance to go through to this underground experimental cavern today, as it is completely locked or sealed off today, waiting for the beams. But this is how it looks like. So we have two big underground caverns, the service cavern and the experimental cavern, and they are separated with a huge concrete, more iron than concrete, to tell the truth, pillar. This is something like 7 meters thick. Actually, there is nothing very special design parameter for this, just to hold mechanically the two big caverns in this very, very soft soil where we are, or very soft rock where we are. The side effect of this pillar, however, is that it works like a very good shield of radiation. That results in a fact that in this service cavern, in this region, what I'm showing you, you can take visitors any time of the year. This is very, very, very special. All around on the LHC, we are the only experiment who can take visitors underground. And obviously, once we open the detector for the visitors, there is a passageway that opens for them for that time. What you might see, the non-hedged area is the accelerator tunnel. You might imagine it cuts through the experimental cavern, cuts through the detector, but there is another gallery, underground gallery, that was excavated for this kind of activity. You might imagine that if you have to transport something from here to here, you cannot take it through the detector, so you need a bypass tunnel. That's the bypass tunnel that goes on the one side of the underground service cavern. We have a secondary elevator that we don't use normally, but it's there if we have to evacuate people and the primary elevator is inaccessible. What we all have to tell you, while Noemi is out, I don't know why, we have to tell you that we are very keen on the safety. Even though this experimental area is not more dangerous than the tube in London, we don't want to afford any safety violations and any resulting accidents. If this would happen, obviously we would land up on the front page of the leading newspapers on this globe. And even though we like to land up on the front page of these newspapers, we don't like this topic to be.
We like to be on for the right reason.
Exactly.
For discovery or new progress in our field.
That's absolutely correct. Noemi, do you hear us, by the way?
Yes,
exactly. So I think I would give it back
technical
to
problem.
you.
Yes.
But are you over with it?
Yes, it seems that the new stabilizer doesn't like the magnetic field.
Oh, even in that size.
Even here, yes. So we had to go back to the old one. So okay. Yes, this is the safety area in level -2, as you mentioned, with 2 big fire doors. And just to prove that we are really underground, I can point the camera up, because this is a vertical shaft. I think, Zoltan, you mentioned it in the shared image, that we have the elevator shaft, and maybe you can see the top of the shaft, the roof on the image. So we are about 90 meters underground from the surface, and left is the elevator shaft. And what you can see bit down, this is level -3, so we are at level -2, and this is the bottom of the shaft. That's 97 meters underground, and
that's the ground floor of the experiment.
Very yes, and what you see, that there is a movable wall there. It's really a movable wall, and when we have the winter shutdown or the long shutdown, which is for many years, when we have access to the cavern, this is a point where we can transport heavy, big elements underground to the experimental cavern.
At least one of them. This
is one of them, yes. And I don't know if we should
We
show
not yet
some.
talk about the detector itself. I have an insert for that while you are just going through the nice pictures. I would need to start with a confession. You all know that there were Nobel Prizes awarded for the discovery of the W boson, Z boson, and finally the Higgs boson 10 years ago. But the subject of the confession is that there was nobody who saw them flying through the room. And the reason for that is that they are extremely short-lived particles. Their typical lifetime is somewhere around 10 to the minus 23 seconds. The 23 is an interesting number because if they would fly at the speed of light, they don't do, but if they would, the speed of light is, as you know, is 3 times 10 to the 8 meters per second. So if you multiply these two numbers, you would get something like 10 to the minus 15, which is characteristically the size of the proton. So that means that these particles, even, well, they are created. We know that they are physically existing something, but as they not able to emerge from the proton beam, if they are created, there is no chance to see them directly. However, what we can see about them is their decay particles. And then from the observation of these decay particles, we can reconstruct, we can mostly reconstruct, or we can have a hint what happened when these particles were created. So the observation of the particles, what do we have to observe? Obviously, we want to know where these particles flew away. Let me just show you something like this. So we have to, this is something, if we would want to visualize what happens inside, I know that this event, as we call, is something that survived all the tests, all the cuts, as we call, for the Higgs analysis. And we believe that with a high probability, this was a Higgs event. Higgs decayed into two photons, well, to two Z's, then two photons, and two muon particles. By observing the two muon particles and the two photons, we could reconstruct the mass of the Higgs boson, the invariant mass of the Higgs boson. And if we observed quite a few of these events, we could have a statistical analysis on this parameter. Obviously, the whole process is a lot more complicated, but let me just explain it in this simplified way. But that's mostly the way as we work. So we observe these particles. What do we want to observe of these particles? Obviously, we want to know where they flew. Obviously, what we wanted to know, especially in the muons, what is their momentum? We want to know what is the energy of the particles in case of the photons. This is simple. You want to know the photon energy. Also, you want to know where they flew away. And also the fourth thing, you want to make distinction of the particle identities. So you want to know what was a muon, what was a photon, what was a pion, what was an electron, etc. So in order to do that, you have to make a quite complex detector. One explanation is that among these four parameters, at least two are incompatible with each other. If you want to know where the particle flew, what was the flight path, obviously you want to measure the flight path without interacting the particle. That's true that the detection itself is a kind of an interaction, but you want to minimize it. You want to keep it to minimum. On the other hand, if you want to measure the energy of the particle, probably this slide is much better. So if you want to measure the direction, you do not want to interact because you don't want to have an effect on the particle flight path. But if you want to measure the energy, you want to stop the particle, you want to take away all the energy it takes. So obviously you cannot use the same type of a detector. I was a little bit slow on this. I was wondering a bit, but in general, you can claim that you can't use the same type of detector for these two processes. That tells you that the detector has to be sufficiently complex in design. The innermost part is a detection of the flight path, as we call it, tracker. Today, this technology is based on silicon, based on PN transitions. The innermost part is a pixel detector. We have, I think, 80 million pixel individual small detectors in this. 80 million is not a big number. Even my phone that I bought quite a few months ago, one of the cameras is a 200 megapixel. The difference between this and the 80 million pixel detector is that while my 200 million pixels are on one plane in order to make a two-dimensional picture, the 80 million is made on four concentric cylinder surface, therefore able to create a three-dimensional picture. And while my camera can make, even in burst mode, can make probably 10 pictures per second, this little toy that we have down there can do 40 million pictures per second. So obviously that's the difference. And this is only the first 4 layers. The next, I think, 10 layers is also silicon detector, but strip detectors in order to keep the channel number to the minimum. Otherwise, we would not be able to read them out. Today we would, but at the moment when we designed these detectors, we couldn't. So this is quite a sophisticated tracking detector. Outside the tracking detector, we have colorimeters. In the CMS detector, we have 2 different types of them. The electromagnetic colorimeter that is sensitive for electrons and photons is built up of crystals, lead tungstate crystals. We have something like 77,000 altogether, just a few of these detectors. These detectors are not sensitive for those particles that have quarks inside, hadrons. For them, we had to build another dedicated detector, the hadron colorimeter, that's made of brass. Both detections are based on particle shower generation. Slightly different physics behind, but every single incident particle that comes in creates a lot more secondary particles. And in case of the electromagnetic colorimeter, through these microphysical processes, we create photons. That's why we have crystals. And these photons we channel together, we measure the overall intensity, and from this we can conclude what was the incident particles energy. In case of hadrons, we do something very similar, but we need something heavier. Therefore, we use brass. The brass has one simple problem. It's not transparent. Therefore, what we could do, we sliced the brass up, and we interleaved with these slices with scintillators that just make a scintillation when a particle passes through. So again, we bring back the energy measurement of measuring intensity of a flash. This is a kind of from this, the morphology, this is a sampling colorimeter. We take samples of these showers, but this is sufficient at this moment. What we can tell that the 2 colorimeters together eat up the particles. They are designed quite well. That's one of the design parameters that governs the size of the detector, the colorimeter itself. We have to fit in the colorimeter with the particles. But the result is that we don't get too many particles passing through the colorimeter's external shell. Only 2 types of standard model particles might pass through. One is the neutrino that flies away, that interacts only weakly with the matter, and we are too light to tell the truth to make any interaction with them. we conclude their direction and momentum, postulating the momentum in energy conservation. That's so far quite established, so we can use these two, well, one law of nature to conclude where the neutrinos went through. And so the supersymmetric particles and the dark matter, if they exist. But okay, I do not want to go in this direction today. And apart from the neutrinos, there is another particle that might pass through, and that's called muon. You know that the muons might pass through hundreds of meters of rocks. Even in the detector, we see cosmic muons. With the cosmic muons, you can make measurements on the pyramids as well, the inner structure. You can make measurements on the oil fields. You can search for oil and gas in the soil with muon tomography. That's the word that I was looking for. So indeed, that's a quite powerful particle that passes through our detector, that punches through, so flies away. But as it is electrically charged, it can make an ionization. And this ionization that we use in the so-called muon chambers here, these are gas chambers with high voltage cathode wires or strips or whatever, or even holes. And due to the ionization and due to the high voltage, we have an amplification of the secondary particles, therefore we can read out. We can have, this is also a tracking detector, we can tell where the muon passed through. And this is quite an important thing. That's probably the reason why I'm talking so much about the muons. I just mentioned that practically only the muon can pass through. So it means that what you see here is very clean. You can make a decision to take the data. The problem, yes?
Sorry, Zoltan, for the interruption. You asked me a reminder, so we have almost 20 minutes left.
Oh, sorry about it. Noemi also wants to tell something. I would say that in this point, I would stop discussing about the detection, as we could continue. You know me, we could continue it for days. I would rather ask for the questions on this, but I let Noemi to talk rather. Noemi?
Yeah, do you hear me?
Yes.
Okay, we went to the end of the service cavern just until
I was talking too long. I apologize.
So this is another access pad. This leads to the experimental cavern. Maybe you can share, Zoltan, the picture. So maybe you can see through that there is a small corridor which leads to the detector.
Yes,
cavern.
let me just put it in.
And this is the unfortunate that no entry. And just all the frightening signs are on that nobody can just go in. Yes, so we are here and we just prepared some fun stuff. Since you mentioned the magnetic field, that we have a very strong magnet for particle detection, but even we are at this 7-meter thick wall between us and the detector, and also the services. So we are about 10 meters away from the detector, but we still can experience the residual the rest of the magnetic field, what is from the solenoid magnet. So we bought some very expensive magnetic detectors. So these are paper clips made in a chain and attached to these screws, and you could really feel that it is defying gravity. And this is because of the magnetic field. And we have some other cable chains as well. It's pointing towards there.
I just would like to talk about numbers while you are showing these extremely nice things. inside the detector, where the colorimeters, the tracker are, we have 3.8 Tesla field. That's not extremely high. Even in the MRI machines, you have something similar. The only difference is that while the MRI bore is something like 70 centimeters, we have 6 meters. Therefore, we are bigger, indeed. What Noemi experiences as a field strength, we measured a couple of months ago. This is something like 10 millitesla. So we are at least 300 or something like times less than the inner magnetic field. And this is strong enough to, yes, exactly, to play these very spectacular magnetic games.
Yes. So since we have not so much time, we would like to show you in the underground our counting room where we have our electronics for the detector.
Okay,
And
go ahead, Noemi.
we just collect our our toys. So it's really, really nice. And yes, let's show why we are going away. So it's really a small field. And here we don't really see that we are a bit away from the wall. And here it's really, really a very
probably
low field.
that's the moment, that's the point where it becomes vertical completely.
Yes. So we have a so-called counting room where we have electronics for our detector, those which should be closed, but not in the experimental cavern. And this cavern is always accessible even when there is beam. So we have some high voltage modules for powering the subdetector. In these big boxes, this is also high voltage. We have some optical fibers, which is data taking for the data signals. And of course, I work for CMS, but I don't know all the details of all the cables, only the experts.
You probably heard the music. This is something, a code language. If the DAQ stops for any reason, if it collapses, we have this sad music.
Yeah, and this is I know only from because it's written there that this is for pixel subdetector, and I think that I could talk about it quite a lot because he's one of the experts of that. So we have units for data taking, for trigger system, for controlling, yeah, lots of things. We have also computers. I can probably show these nice rack mount PCs.
But obviously we do not install them very close to the wall.
Yes. But again, power supply. And
so usually a power supply is the device that you cannot take arbitrarily far from your detector. Obviously, it would induce quite a big losses, but you cannot take it very close to the detector even, as it is sensitive only for two things. One is the radiation and the other is the magnetic field. So usually the power supplies, especially the power supplies, are far away from the detector.
And may I show one picture?
Yes, my favorite.
Yes. So this made in 2000 or 1999 when all the CMS started to all the excavation work in this area. And since it is a place where were the ancient Romans quite active, so the Roman Empire was also here in this place in Europe, the archaeologists had to come to the site before any work, and they found a Roman villa and some coins and some pieces of artifacts. And what Zoltan say, I think I let you to say.
So what I used to say is that you see that even the ancient Romans knew that this is probably the best place in the universe.
And this is some picture from the excavation work of the shaft. You can see the size of a man. So also here in the back. So it is quite large.
Quite
quite large. And you mentioned that we had to build up the experiment in the surface.
No, I had no time. I talk too much. This is probably the last picture I would like to let you to show, and then I would ask for questions.
And then I go upstairs in this case.
Yes, please. Yes, please.
Okay. See you soon.
Right. So actually, I'm just ready for answering whatever I can.
Any question?
About how much power was it 3.8 Tesla? For the magnets?
You asked how much power is in that, how much energy is stored in that field?
Yes.
2.2 gigajoule.
So there's an interesting metric about the gold, but I forget.
Oh yeah. You know that I don't recall how many kilograms of gold could be melted. Probably I cannot even imagine. I have never seen so much gold in one.
Yeah.
But what I heard about that this energy is comparable to the kinetic energy of a B747.
Mm-hmm.
And we all know, unfortunately, what changes it might make to the landscape when it's crash landing. Obviously, we don't want to have a B747 crash landing on the ground. Therefore, we make everything, every possibility to bring out this energy in case we have to. We have a quench protection system. I mean a device. I mean a very thick copper rods, water cooled, where we pump this energy up on the surface to a resistor network where we dissipate it away. That's quite a bulky stuff. Noemi can probably show. She's not very far from the quench bars. If you could show them.
Yes, I try, but I have to make some light.
This is what we call remote control, you know.
Mm-hmm.
That's on the other side. Don't go to the other side. You can see it from here. Oh yeah.
Yeah, but I need light.
Oh yeah.
Okay. Maybe from this view.
Yeah, exactly. You see something comes up from below and turns below the green grid. These are the quench bars where we pump up the energy in case we need to. Fortunately, this year we didn't need to use it. We are so fine, and we try to avoid even this thing. Don't forget that if the field collapses inside the magnet, it creates quite a huge dynamic of forces that might lead to the fatigue of the mechanical system. And after a given number of these so-called fast discharges, we have to trench the magnet. This is something like 400, and we are only at the fraction, fortunately, as we don't have any spare part of the magnet.
There's a lot of energy stored in that field.
That's a pretty huge energy.
Yeah.
Thank you.
Attention, inject warning received.
Okay, another question.
What discoveries from CERN have helped improve our understanding of energy, matter, or the fundamental forces of nature?
I heard something about, it's a little echoey in your room, sorry, but I heard something about the challenges with certain measurements like quantum entanglement of particles.
So, but discoveries from CERN have helped improve our understanding of
I mean,
energy.
So we make a
or
lot
fundamental forces of nature.
fundamental forces of nature. Gotcha. I mean, we make a ton and a ton of record-setting measurements on all the time, and it's a bit fatiguing because we can't keep publishing that like a new record has been achieved. And when I say a record, I mean a more precise measurement on some of these particles. So we've made quite a lot. The one we always talk about is the Higgs boson, and the reason we talk about it is because the Higgs boson particle proves that the Higgs field exists, and that Higgs field existing answered a lot of questions we had about the fundamental interactions of our particles and why they have mass and things like this. So in that same vein, we make measurements on the rates that certain particles are produced, some of these exotic particles. And that also confirms that our equations and our model is correct. We also, and we do it on crazy scales. So what I mean is we have our model or equations that predict these particles being produced at all these different energies and all these different cross sections is what we say is our like technical term. But every time we measure it, it's pretty dang consistent with our standard model equation, which is, we're happy that we do that, but we're also a bit frustrated because we're trying to see something new, something that is not explained by our standard model. So yeah, we're making all these measurements that some confirm new things like the Higgs boson, some confirm the model that we know, these more precise measurements. We're doing all these things all the time. It's hard to put it in perspective because there's thousands of people working on these, this experiment and these analyses. But if you want to know about things we're looking for, we mentioned supersymmetry. So we consider, some people still look for this, I look for this in my analysis, where there might be double the particles, but those extra particles are completely invisible. So what that would look like in our experiment here is in a very certain like subset of your collisions, very specific collisions, it would be like you collide and then quite a lot of stuff disappears. And that's kind of a weird thought, but you can imagine it. You collide and it's gone. Not all of it, but a good amount. So yeah, that wasn't your original question, but we look for these new physics here, and we're hoping at the end of run 3, we'll have enough data that maybe we make another discovery or something.
I just would like to add something to this. We all know that there are 4 fundamental forces. Well, maybe 3. Well, okay, I do not go in that direction. So let's assume we have 4 fundamental forces. The question might arise, why 4? Why not 3, 5, 6, 7, 40, 42? What we think that when the universe was created, these fundamental forces were not distinguishable from each other. And as the universe cooled through a so-called spontaneous symmetry breaking processes, these forces became distinguishable from each other. And this was something, a theory that I would say blew the fuses in some people, but there was a prediction that at a sufficiently high energy, you will not be able to distinguish, or you can, well, mathematically, you can use the same formalism on the electromagnetic and the weak interaction. And we have already reached it, and we discovered those particles that are predicted by this unified approach, the W's and the Z's, and I think this was one of the groundbreaking thing. Also, the Higgs was part of this kind of thingy. Now we think that at some point the the strong and the rest, these electroweak, would unify again. That's the the grand unification theory. We also hope at some point, at someday, we will reach it. Probably these energies that where we are pretty low. But actually, this is something that we have already started a step on, and we already saw the first process, even if it is extremely weird. The Higgs mechanism is not something we would expect with the everyday thinking. Right.
We're a bit over time.
Yeah, a bit, but I let them to ask more questions or conclude as if they wish. Any more questions?
More?
What is the Higgs boson?
What is the Higgs
The Higgs
boson?
boson. The Higgs boson is the elementary excitation of the Higgs field. Sorry, that's the answer. The Higgs field is so what we think in the quantum field theory, that each of the particles have a field associated. The Higgs field is a very interesting field, because this can create the masses of the particles. The interaction with this field gives mass to the particles. The Higgs boson is the elementary excitation of this field, just like the electron is the elementary excitation of the electron field.
Yeah, there's many ways to answer that question. It is quite hard to put it at an appropriate level, but you can imagine the way our mathematics work in this field is every particle has a field associated with it. And this is why particles are waves, because they're like a ripple or an excitation in this field. And so the Higgs field was proposed many decades ago as a theory, and it answered some questions, it solved some problems with the other fields. But again, you can never know that field exists unless you can produce a particle of it, a quanta of it. And so that's what the Higgs boson is. It's an excitation in that Higgs field. How do we know it is the Higgs boson? Because in the math of the Higgs field, you can predict it would be a spin zero particle, saying some jargon, but a spin zero particle, it's neutral in charge, it has a mass, roughly, we could roughly put some error bars on what the mass should be. And so
well, we couldn't. I remember from my PhD thesis that I was
retroactively we think, yeah. Well, yeah, of course, obviously it was in this range, but so when we observed a particle with those properties consistent of the particle of the Higgs field, that's how we were very confident that this is the Higgs boson. And then you can measure, we keep producing more in our collisions, and we continue to measure more of these properties to be more certain that it is the Higgs boson. And so far, it's very consistent with what we think. And
before we would blow the fuses, I would like to calm down the nerves. What we are talking about are models. We don't know how the universe works, but we want to be able to predict what will happen if you design an experiment. That's an absolute must. In order to make a prediction, we make models, we make theories. One of these theories is the quantum field theory that requires these fields, the elementary excitations as known as the particles. I think what we can claim that we can make usable predictions with this mathematics. We don't know what is the underlying physical process. We don't know how physics works. We don't know what I can imagine that that the universe doesn't solves partial differential equation systems. But these mathematical approaches that we use happen to be very successful in prediction of the experimental results. I just would like to to claim for this? Obviously, we don't know.
Yeah, this is, I think what you're saying is like inspiring, like the mathematics and our models, it's, you know, humankind's best attempt
Exactly.
at explaining what you see in these experiments, how these particles behave. It doesn't necessarily mean that they are exactly as we imagine them. They could be doing weirder things that we don't know about, we haven't observed yet. You know, we can't know everything about nature, but we're doing our best.
Very
Yeah.
probably our brain is unable to
Yeah.
completely imagine.
Mhm.
Just an example, particles and waves. Whenever we talk about particles, we tend to think about them as they were balls, like in the pool game. Even I do this mistake, I would say. But we know that you can associate a wave with them. In many experiments, they behave like waves. They have superpositions, they have interference in some cases. When you calculate them in math, it's better to use a wave function.
Sorry, for the interruption.
Okay.
So thank you so much for that incredible talk. We really appreciate the time you took to share your knowledge and experience with us. So it was fascinating to learn about CERN. And yeah, thank you again, Zoltan and Noemi.
It was our pleasure to be here with you. Noemi is here. Mi is örültünk, hogy itt lehettünk veletek. Sorry for the Hungarian language, but as you know, with your teacher, we share a common language as well. We appreciate that we could be here with you today, and at least what was good for this session is to show you that it is a very complex subject behind. Unfortunately, we couldn't touch all the aspects of this, but we tried to make flashes here and there just in order to draw your attention. Thank you very much for being with us today, sorry. That's not my mother. All right, and have a nice day. Ciao, ciao.
Have a nice day.
See ya.